Welcome to the presentation about the limiting magnitude in astrophotography systems and how, and more importantly, how much various factors affect it. My name is Chris Kristanovic. I'm the Chief Technology Officer and the founder of Novolab Observatory. When it comes to equipment, we all strive towards bigger OTAs, better coatings, and higher quality and higher quantum efficiency cameras. But how much do we understand the quantified impact of our decisions? How much do we gain by getting a 90% peak quantum efficiency camera over that of a 60% camera? How much does the XLT or UHTC coating actually get you? And which is better? How do the environmental factors such as the seeing and the light pollution affect you? So the sensitivity of the system, or the limiting magnitude, is the magnitude of the dimmest stellar object detectable by your system. This happens when the target signal-to-noise ratio equals 3. Why 3? Well, that's a scientifically accepted a number. Personally, I actually have a difficult time distinguishing something with the signal-to-noise ratio of 3, so I usually use 5 or 6 personally in my calculations. There are many factors that affect astrophotography system sensitivity, and complete treatment requires very complex numerical simulation analysis. It is important to understand how and how much each of the different elements affect your system. So we will examine the effects of the telescope aperture on the limiting magnitude, the impact of telescope type on sensitivity, the impact of telescope optics on sensitivity, things such as coatings, the imaging camera and its quantum efficiency on sensitivity, and then finally the environmental impacts such as seeing and the sky pollution on the sensitivity. We'll also touch a little bit on the atmospheric extinction, and we'll wrap it all up by showing you how to estimate what your system should be capable of doing. Before we actually start, we should consider taking a step back and right along the beam of light from a distant star all the way towards our imager. So different stars have different temperatures and emit light which peaks at different wavelengths. Your O-type stars are going to be very hot stars. They will be emitting light mostly in the ultraviolet. Your red stars will be mostly in infrared. So if you look over here on this chart, you will see the white line represents the light of a class M0 star, which peaks at about, in this particular case, about 780 nanometers. That light has to pass through our atmosphere, and in process of doing so, it undergoes some extinction due to the atmospheric properties, which is mostly pronounced in the UV and the blue range, and hardly at all in the infrared. Once it reaches your telescope, it has to pass through the telescope, which also has its own transmission properties. This is the purple line, and I believe this is probably a Celestron Schmidt-Cassegrain telescope. Has to pass through the filter. In this particular case, this is some photometric filter, I believe. Reach the CCD or CMOS imager, which has its own response curve, designated here by the blue. And in the end, when you put all this stuff together, this blue line here actually shows you what is reaching your sensor. So out of this area underneath white curve, all that really gets to you is this blue stuff. To make matters worse, there is light pollution behind all this stuff. And here we're looking at this purple curve. This is a typical photochromatic mix of a suburban sky that is comprised of both LED and high pressure sodium lights. And that, of course, also is passed through by the by your filters and your OTA to show you what is actually coming through to the imager. So why do we talk about this background? Well, because that's where most of the noise comes from. There are basically two types of noise that you will experience. Some of it is device generated. Would be your electronics or your read noise, which is the artifact of the physics of reading out your electrons. But there is also noise that depends on your signal and your background. It's called Poisson noise, and it is basically a square root of the number of photons that you have collected in your pixel. We'll talk about this a little bit later, but suffice it to say right now, as we all know, you want to reduce the amount of the background signal. Before we go any further, let's just talk about how we generate all this data. So we use Astrophotography CAD, computation engine, which performs numerical analysis of the entire system. And we simulated it in the full 350 to 1000 nanometer spectral range. In order to determine what is theoretically possible and then calculate deviations from that, we will be using the ideal OTA, being defined as 100% transmission, no obstructions, perfect camera, which has no read noise and has a flat 100% quantum efficiency across the entire band. We will not be using any filters. We'll be using very low haze for the extinction computation. And we'll be also assuming suburban photochromatic sky at 20 magnitudes per arc second, which is equivalent of NELM of 5.5, which has decent mixture of LED and high pressure sodium lights in it. For comparison purposes, we're going to be using a K0 stellar type, and we're going to standardize the exposure to 1 hour total exposure with 60-second subs. And of course, we're going to do all this thing from a beach somewhere in the Bahamas at the sea level altitude. So we all know bigger is better, but how much? So larger OTAs do collect more photons. And if you look on this chart, the blue line represents the ultimate limiting magnitude under the conditions we already specified at zenith that your system can do versus the aperture of the system. Now, this is the theoretical best that can be achieved. You cannot do anything better than that. And you will notice that as the aperture gets smaller and smaller, this curve takes a sharp turn to downwards. And some might think, well, that's because we're plotting aperture and not the area. Even if you plotted the area, it would still do something similar. And the reason for that is very simple. As the telescope aperture gets smaller, the diffraction effects get more and more pronounced. So your star gets blurrier and blurrier, pixels get less light per pixel, and therefore your limiting magnitude starts to go away. And of course, this is an asymptotic curve, asymptotic to the y-axis. So basically at zero aperture, you will have no limiting magnitude at all. But for very large apertures, that slope is approximately 0.06 magnitudes per inch. As you get smaller, this slope increases, but for practical purposes, telescopes that are 8 inches and larger, you can assume average slope of about 0.08 magnitudes per linear inch. So this is what you can get from a perfect telescope and perfect OTA. What happens in real systems? Well, we modeled the same system with the actual camera. So we used the ASI 2600, which has an IMX 571 mono imager, and you can see that all the different telescopes, and we try to get a nice mix of everything from Newtonians and RCs and Schmidt-Cassegrains of all different apertures. They all kind of fall on this one line, which is about 0.7 magnitudes below the ideal. Now, depending on which camera you use, this line might be 0.7 below, might be 0.5 below, might be 0.9 below. It depends on your camera, but that is the general rule. So in other words, in order for you to calculate what your system can see, knowing the aperture, you will start with the ideal, and then you will take out all the losses, which we'll talk about in a minute, and you should end up with a pretty good approximation of what you will be able to do. Telescope type, well, we all know refractors, they basically have 100% clear aperture, so they will experience no loss. But as you start introducing secondaries, this obstruction that increases as you go from Newtonians towards the RCs does cut off some of the light. So in case of the RC, it will cut off 44% of the aperture diameter on average. That will cut off about 0.12 magnitudes of your limiting magnitude. Now, in this particular graph, as you start getting below 8 inches, there's and this is not shown in this graph, the actual obstruction increases from 44% by diameter to more because there is a structure that holds the secondary mirror, but we are neglecting this for the purposes of this discussion. Mirror optics. We all heard of Starbright and XLTs and ultra high transmission coatings. Different manufacturers told these coatings, and they do matter. So, for example, look at the original Starbright coatings. You will see that depending what stellar class you're looking at, they're going to attenuate the signal differently, all the way from over quarter of a magnitude to the best that it will do is about 0.15 magnitude attenuation, and this is just for the system of 2 mirrors. This does not include the corrector plate or anything. It's just the 2 mirrors. And of course, the newer generation of the XLT mirrors, they're a little bit better, and you can see the average went from about 0.2 magnitude to less than 0.15. So they gain about 3/4 of, I'm sorry, they gain about 0.075 magnitudes there. Meade or Orion nowadays, the original EMC coatings were about the same as the XLT today. But the newer generation of UHTC coatings are considerably better. When you go to other manufacturers, they will pretty much use enhanced aluminum coatings, which are on par, I would say, with Meade EMCs. If you have your mirror recoated by somebody that is just going to be doing the protected aluminum, you can see that that's probably not the best choice. It's probably equivalent to the Celestima Starbright on the average. However, for those of you who are more adventurous and want to really, optimize their system, you can go to silver coatings. And as you can see, silver coatings do much, much better, particularly silver enhanced coatings. They almost attenuate nothing at all. And then you have your transmissive optics. Those would be your corrector plates, your objectives, your reducers, and even the camera glass, which everybody seems to neglect that it's there, but it is there, and it does attenuate the signal. So again, not to dwell too much, you can actually see the data here for the Starbright, the XLT, the UHTCs. The magnesium fluoride objective is, a standard coating for objectives, and this is what you will also find on focal reducers most of the time. Enhanced stuff is a little better, but really not hugely different. And camera glass, like I said, it's there. It has to be accounted for. It's on average almost 0.1 magnitude loss there. So, can't really forget about that. I should point out that not too many camera manufacturers give you any data about their glass covers. The exception would be, I believe, the ZWO that actually give you a curve for their camera glass. But in most cases, really, I don't think anybody really cares about it too much. They focus mostly on the electronics. One exception being the newer S-Big or diffraction limited cameras. They really seem to go out of their way to maximize the light throughput through the glass. Camera sensors, well, this is I could do a 2-hour presentation on just this, but I'm going to try to wrap this thing up and be as brief as I can. If you remember that chart of the journey of the photons to electrons, this is your quantum efficiency of, I believe this is CAF 8300 sensor, which peaks at about about 56% quantum efficiency. And it is not across the whole range. It is, peaking at 550 nanometers, but at 1000 nanometers, it pretty much does nothing. So if you're looking at a really red star, it's not going to be very efficient. If you're looking at a G-type star, it's going to be better. And if you're looking at a very, very blue star, again, it's not going to be very good. You could look at it and you can say, well, if I average all this, I will come up with an average quantum efficiency. And in this particular case, it would be probably around 35% or so. But if you look at the sensors from various manufacturers, whether it be Kodak or whether it be Sony, you will find out that the general shape of the curves are very similar. Not necessarily the peak, just the shape. They're very similar because they use the same technology to manufacture their sensors. They're not perfectly similar, they're generally similar. So for the purposes of this presentation only, we're going to do something that is going to allow us to examine the whole range of sensors. So in case of CAF sensors, CAF CCD sensors, we're going to assume the same shape, and we're going to change the peak of this curve from 100% all the way down to 20%, and see how that affects the attenuation that the sensor introduces to your system. So if you had a CAF sensor that was 100% peak efficient with this shape, for example, L0 type star, it would attenuate the signal about 1.25 magnitude. Why would it attenuate it? Well, because it's not 100% across the whole band. In real life, it is about 56%. So at 56%, you can go and you can see that, okay, this is what is this, M0 star, and it's going to be 1.2 magnitude attenuation and so forth. So you can actually get an idea of what this thing will do. And using this analysis combined with the perfect theoretical curve, you can actually figure out the impact of the limiting magnitude. Now, different sensors also have different responses. So if you look at the Sony sensors, whether they're CMOS or CCDs, you will see that they actually have a pretty good response in the blue. They're really skewed towards the blue. So if you're looking to detect very red stars or brown dwarfs, Sony is probably not going to be your best choice. Looking at Kodak sensors and G-Sense CMOS APS sensors, they're much more broadband, obviously not perfectly flat, and their response is skewed a little bit towards the redder, which gives you a better balance between the blue, very blue, and infrared. So let's look at all this data and let's compare some cameras and some sensors actually. So looking at a perfect sensor up in the table, you can see the average quantum efficiency of 100%. The G-Sense 2020 backside illuminated sensor actually has an efficiency of 6%. And you go all the way down towards the CAF 8300, which has the average efficiency of 34%. So if you look at the bar chart of all these sensors, you can actually see where the perfect is. You can see your G sense over here at 22 magnitudes. And this is, of course, for the Astrotech 10-inch RC OTA. Not ideal. This is the actual real OTA. So you will see 22 over here, and the CAF 8300 is 21.7. So basically half a magnitude difference in limiting magnitude between these two sensors. And if you notice that as you decrease the quantum efficiency, the limiting magnitude drops off also. So you can go and plot it, and you can find out, hey, as I increase the quantum efficiency, there's a general line that these things can be fitted on. And the slope of this line is about 0.011, in other words, 11 millimagnitudes per percent of quantum efficiency. Now, not all the data fits neatly on the line, so this point is way off. And this point actually happens to be the CAF 1602 enhanced sensor. So why is that not on the line? Well, pretty simple. The read noise of that sensor is 15 electrons, whereas your G-Sense sensors and your newer IMX sensor from Sony, they're like, a couple of electrons. And this read noise affects things quite a bit. So, this particular point and these two particular points of here, which are also CAF sensors at 16200 and 8300 CAFs, they're going to be way offline over there. So, in essence, and this, of course, again, I'm going to emphasize, this is done with Astrotech 10-inch RC under the 20 magnitude skies and a 2 arc-second seeing. But if you change to a different telescope, so you go to 16-inch RC or 28-inch something, or Schmidt-Kessler Green, any telescope really, the slope of that line is going to be the same. The limiting magnitude is not going to be the same, but the slope is going to be the same. So remember that 11 millimagnitudes per percent average quantum efficiency. That is a useful number to know when you look at the average quantum efficiency of different sensors. So, going from this one to this one, you can kind of figure out, hey, this is like 17% difference times 0.011. You can kind of figure out roughly what it is going to be for a K0 class star. So we also know that seeing is a major factor in what we can detect. Seeing blurs our image in a big way. So some people who live under very, very nice clear skies might have a seeing of half an arc second. Some people live in the areas like where I live, which is between 2 and 3. But if you do the analysis, you will find out that this curve over here is really what it looks like. And if you look carefully, you will see the 1, 2, 3 arc seconds seeing that, but equally spaced out. So if you look at these curves, you will see that they also are asymptotic to the y-axis. And it's pretty easy to explain why that is. As your aperture gets smaller, the diffraction properties of the telescope start to be very large as compared to that of a seeing. So, what difference does a one arc second seeing make if your area disk is 5 arc seconds? It doesn't make much difference. So if you look very carefully here, if you look at where the knee of these curves is, so this blue one, which is half an arc second, the knee is pretty much higher in aperture than it is for the 3 arc second, which is down here somewhere. And the reason for that is half an arc second is very noticeable to a 10-inch scope, whereas it's hardly noticeable at all to a 2-inch telescope. So that's why this thing turns down. But that said, you can actually plot the the impact of the seeing on the aperture of the telescope. And if you look over here on this chart, which is exactly what we did, so the limiting magnitude loss per 1 arc second of seeing change is, on average, for most of the system, is going to be about 0.33, 0.34 arc seconds, magnitudes per arc second of seeing. It's a good number to remember. And of course, this gets to be smaller and smaller as you as your aperture gets smaller and smaller. So your guiders are not going to be really affected by seeing very much at all. And then, of course, we do have your light pollution impact. So we have here an example of skies going from 18 um, magnitudes per arc second all the way to 21 magnitudes per arc second, which is a pretty nice dark sky, and in one magnitude increments. So if you look at it, they're equally spaced. They again do this little turn like we did before, and the reason is the same. But if you actually plot this versus the aperture, what you will find out is that it really pretty much stays constant with aperture. Notice this is half a magnitude per arc second. This is 0.49. So there's very little difference really between this one and this one. So, for general purposes, assume half a magnitude loss for each 1 magnitude per arc second of sky background increase or decrease. Now, I'm just going to take a step back and talk about a noise a little bit, why that is important. Yeah, I mean, you will have a background of so many electrons in your well, and all the software you have nowadays can subtract that. But every time you make a measurement, there is an uncertainty associated with it. This is called Poisson's noise. So 10,000 electrons in your well, irrespective of where they come from, are going to have a noise of square root of 10,000, which is 100 electrons, which is a problem if you're trying to detect a star that has 100 photons. It's really not, you're not going to be seen. It's going to be one-to-one signal to noise. It's going to be noise. But if you reduce your background to only 1,000 photons under dark skies, the resulting noise will be only a square root of that, which is 33 photons. Now that will give you signal to noise ratio of 3 for the same star of 100 photons, which makes it a detectable object. This is a fairly simple way to look at things, but in reality, things are more complicated because the objects themselves have stars and there is a dark current and a whole bunch of other stuff that contributes to this. But simplistically speaking, this is where your problems come from. And finally, the extinction effects. Now, extinction basically is your atmosphere attenuating the light. And it does this thing by means of various factors. There's a thing called Rayleigh scattering, aerosol scattering, or haze, which is defined by the atmospheric optical density coefficient. And then there's also the ozone extinction. Put them together, you get your extinction. And it depends very heavily on the target elevation above the horizon. So if you're really low to the horizon, you're looking through a whole bunch of air, and your extinction is going to be very heavily impacted. It's also going to depend on where your site is. If you're on top of Mount Everest, there's a lot less air to look through than if you're sitting on the aforementioned beach in the Bahamas. So, if you look at this chart over here, as reference to the zenith, when you look at a 60% elevation, you will see the O-class stars have a fairly low extension of only 0.05 magnitudes, and your L stars basically nothing. The average extinction across the oldest L classes is about 0.025 magnitudes, almost nothing. But move down to 30%. Look at the change. It is massive. But infrared stars, again, very, very, L0 stars, hardly any effect whatsoever. And this is going to be true pretty much no matter what you do. So if, and going below 30%, this rockets astronomically. This really takes off. So, at least for me, I never even consider looking at anything below 30% unless it never ever shows up about that, and I have no choice. And even if that's the case, I usually use filters that eliminate the blue wavelengths. So let's put it all together and see what we can do with this. How would you estimate a system, a limit magnitude of your system? Well, you start with that first chart, the theoretical. And that's assuming that you're living under 20 magnitudes per arc second sky and 2 arc seconds of seeing. You will subtract the OTA attenuation. So if you have a Schmidt-Castle grain, it will be 0.063 magnitudes. You will subtract the attenuation due to all relevant optics. So depending on what kind of mirror your telescope has, what kind of corrector plate, what, if you have a camera window, if you have a reducer, just use the assuming it's like an objective. And then, of course, you subtract the camera attenuation, as we discussed earlier, for selected stellar type, bearing in mind the peak quantum efficiency of your sensor. And in this presentation, we had only provided data for the CAD sensors. So if you have anything else, this will only be very approximate. If you don't live under the 20 magnitude skies with a 2 seeing, if it's different, you will subtract or add half a magnitude times the difference from 20 magnitudes per arc second. And if you have a seeing that's not 2 arc seconds, you will do the same thing using 0.32. So if your seeing is 3 arc seconds, the difference is 1. You will subtract 0.32 magnitudes from that graph. If it's 1 arc second, the difference is, in this particular case, -1. You will add 0.32 magnitude. So in other words, you will be able to see better. And the result will be, an estimate will be typically within plus minus 0.15 magnitudes of accuracy. If you need more accurate results, well, that requires a lot more complex analysis and a lot more in-depth treatment. I want to thank you for spending your time with me. I hope that you will find this presentation useful in your work. Do visit us at our website, nlobs.com, where you can find more information about astrophotography CAD. If you do have any questions or comments, feel free to contact me directly at this website below. There's a contact form there, because I will not put my email address out here on YouTube. Until then, clear skies and enjoy your hobby. Thank you very much.